everybody. Yeah, apologies for starting a minute late. Just while I finished eating. Okay, so welcome to week four of building a GIF decoder. Now, I felt like last week I was really confident we were going to get there. We were just finishing off our LZW decoding information, the decoding code, whatever. And I thought we'd get it right first time and we'd get the proper image on the screen and it would be awesome. But that didn't happen. What we've got instead is this kind of splat. Let's zoom this in a little bit. No, I can't seem to zoom in with the mouse. Okay. This is not a picture, an animated picture of a cat being brushed. I think we can all see that. So, what has gone wrong? What has gone wrong? That is the topic of today's episode. Now, I have last week I had a couple of little notes set aside for how GIF and LZW worked, so I could just quickly have a look and make sure I was not completely off track. This week, I have to confess, I've actually been through and debugged some of this stuff, just try and find some of the bugs. So we'll look a little bit into how I found these bugs, but yeah, it won't be. This is more of a reenactment than me actually finding the bugs for the first time, because I figured that me just staring blankly at something, thinking why was not a great value entertainment. So, what did I do? One of the first things I did is I found this page, which is part of the documentation for a library called GIFlib, and it's what's in a GIF, and this talks about this goes through exactly how a GIF works. Which is awesome. And one of the things that it comes with is a little sample GIF, which you can see I have already added. I've downloaded. Let's change our code to load this up, because we have here, we know exactly what the bytes are. We know how everything should be decoded, what everything means. Whoops. Wait, and we also know how to turn this into the actual output codes, into the the color indices to actually draw the image. So let's go ahead and change our code so that instead of loading up the cat GIF, we're loading what was it? Sample. Type sample one.gif. Let's just check that. Sample underscore one. I'll close that again to give us some more screen space. So, what happens when we run this through? It's not quite right. Not quite right. Let's zoom that in again. So it looks like we have just one line, and it's red, blue, red. I'm colorblind, so. But yeah, so we have red, blue, red, but there should be a gap in the middle. What's going on? So we can actually step through as we get each code and see whether it matches. Now I'm going to just assume that the rest of the information we're getting is all good for now, and instead what we'll do is we'll just look at the actual LZW codes that we're getting. Let's not have that. So when we come in, we know from this, let's pull this off to one side. We know that when we are doing decompression, that we should expect certain codes. our first code should be a 4, which is our clear code. Our code is 4, and that is the same as our clear code. Awesome. Great start. Now our code does not equal... okay, so this is looking for the biggest code we can currently deal with. It's saying, okay, so the code size shifted up... Oh, sorry, 1 shifted up by the code size gives us a number that is 1 bigger than we can currently represent, and then we minus 1 from it. That tells us what the current biggest code we could read is. So if we're reading in 3 bits of code, which we are at the moment, 3 bits gives us 8 possible values, 0 to 7. So if we shift 1 left by 3, shifting to the left is the same as doubling. So 1 becomes 2, then 4, then 8. Okay. And then we minus 1 to get 7, because 7 is the highest value we can currently represent. Okay, if we get that, then we need to increase the code size, but the code size can't go above 12. This is something we did last week. Here, like, that's not going to matter. Is the code our clear code? Yes, which is correct. So we clear, we get a new code, we go through again. Code is 1. Awesome. Oh, excuse me. I wish I could have found the mute button a bit quicker there, but I have no idea. Oh, it's over there. I'll try not to sneeze on the stream again. So our code is, this time is 1. Because I can just... which is correct for our next code. Let's just go through and we'll see what codes come through and see if it's correct. So we get a 1. And then we get a 6. Awesome. Correct. Then we should expect another 6. Yep. And then a 2. And then a 9. Only we're actually getting a 2. And long story short, I'll explain what I worked out about this. This one, it was driving me a bit mad for a while when I was looking at this. But this whole check is in fact wrong. This is saying if the next code I read is the biggest one that I could possibly read, then I need to increase the code size. But that is not what it is meant to be. Instead, in each turn through the loop here, I add something to the dictionary. I add a new element to the dictionary. And it's this that causes the problem. The next time, once I've added in the highest dictionary item that I could possibly represent, that's when I need to increase the code size. Because my dictionary has outgrown the current codes. So let's give that a bit of a change. So here, instead of doing this check here when we read in the code, instead we'll move this down to over. So these are the branches where we update the dictionary. So over here, and we say that if and we're not actually looking at the code that we've read. We're looking at the item we've just added to the dictionary. So this dot next, we want to know when this dot next became the highest thing, when the last item added to the dictionary became the highest thing we could represent. But because we have this plus plus on both times when we add it, we actually need we're actually looking to check when it has gone over that. So we want it to be the highest thing that can be represented by a code size plus 1, which is actually this. So code size will go up, and we'll still do our check to make sure that code size doesn't go above 12, because GIF spec says that it can never be more than 12. So now let's see what happens. So we start again. We get a 4, a 1, 6, 6, 2, 9. Awesome. And then a 9, and then a 7. And do we have any more input here? No, this is as far as it... oh, hang on. The final stream would look like 997. So we can go through and just check everything. So we're going to have 8, then 10, 2, 12, 1, 14, 15, 6, 0, 21, 0, 10, 7, 22, 23, 18, 26, 7, 10, 29, 13, 24, 12. Yeah, this looks like it's working. 12 and 5. But that still doesn't look... That doesn't look right. It doesn't look right. So our LZW decoding is working perfectly now. We're getting exactly the codes that we expect. So what is our next bug? There's another one. I'm just gonna tell you this one. This was one that I noticed. I just saw this bit of code and thought, why is it that way? And it turns out it's because I have no idea. So here, when we're filling out the dictionary to start off with, so we want the dictionary to contain, for each index, initial index, we want it to represent a sequence of colors, a sequence of color indices that is one item long. So it's saying that this item, dictionary 0 will be an array consisting of one item, which is a 0, etc., all the way up to the clear code. Now we don't want to overwrite the clear code. We want it to be everything up to the clear code. You can see here that I've done less than, so that it doesn't get to clear code, but also -1. So the dictionary is has incorrectly been built, which means that we're actually, if we try to read out the item which has the index just before the clear code, so in this case it would be if we read a 7, we're going to read out an undefined instead of an array containing a 7, and we do in fact have a 7, which we are supposed to be reading. But that isn't the bug that's causing it to look wrong. The bug that's causing it to look wrong is also that I just misread the spec slightly. I misread the spec slightly, and I actually said last week that I thought I was doing it wrong. So when we have a new code that we haven't, that we don't know about, we create that code in the dictionary and then immediately return it. And we do it. What we do is we take the last thing that we got, and we take the first element of the last thing we got. And we're supposed to do the same thing when we do find it, except instead of taking the last one, the last item, the last thing returned twice, we take the last thing we returned and the current thing, and it's the first element of the current thing. There's not a very clear way of saying it. So if last time we returned white, red, and this time we're getting green, blue, then instead of putting into the dictionary white, red, green, blue, we should just put in white, red, green for some reason. And then next time, because the last thing is green, blue, the next thing will be green, blue plus something. Okay. Well, that helped us. Yes. So now we have the correct image here. Though I suspect that we also have some other bugs to deal with. So let's go back to our cat. Cat.gif. And this still looks pretty wrong, but if we look at what it's supposed to be, over here, you can actually see we've got the top of the brush here, and we've got the edge of the sketching post. Some of the information is now correct, which is pretty exciting. Now we just need to see how to get the rest of it out. Yeah. So that's pretty exciting, but it is still not an animated GIF of a cat. Now, one thing that puzzles me, which I haven't found out in my debugging earlier, is why we only get the top part of the image. So I don't know if you see, but if you remember, but what we're actually doing is at the end of all this, once we've got all of the image data and we've drawn it, I'm actually throwing an error because I didn't want to. So this GIF consists of many images, which is how the animation works. There's many images in a sequence, and we've got a really inefficient way of reading it and drawing it. So this was just to save us some CPU time. But you'll see that ending early is not why we have an issue here. So if this ever ends... Oh, I hope I haven't messed up the sound again. Do let me know if the sound has gone wonky. Oh, this may take a long time. Okay. So you can see that even when we get through a load more of the file, we're still only getting the top here. I think we're partway through a line here. Let's get through to the end again. Where are we? So let's get through to the next time we get there. And you can see that we've still only got the top of the image, and it is the top of the image. You can see the top of the scratching post just sort of coming through here. And if we go through to the next time we get that, again, so we're getting the top of individual frames. And one thing we can see here is that we decoded this data, and we are getting 16,351 color indices. Okay, so when we concatenate them all together, 16,351 indices for our color data. But our image should be 480 by 480 pixels, so we should be getting 230,000. So what's that? 16351 over 230,400. We are only getting 7% of our image. 7%. And weirder, so the sub-blocks that we actually read, so the image bytes that we're decoding is 126,000 bytes long, but we're decoding that to only those 16,000 indices, which is pretty bad compression. So it seems like we're stopping early. That's something we need to investigate. But before that, let me just have a quick check if there were any other bugs I found. No, that's basically where we're up to. Oh, there's one more thing. Earlier on, when we were in our first week, I passed out a bunch of data, and I was just like, oh, we'll just read it and then like ignore it. Like we'll find out if we need it later on. One of the things that we read was a graphic control extension. So we actually read out these fields: block size fields, delay time, transparent color index, disposal method, and some of these are important. Particularly the transparent color index and transparent color flag. We should use those. We should use those straight away. Now the graphic control extension, I believe, sets values just for the very next image, but we should have one for each image. So I'm going to set this as something on the class, on the GIF class. So this is, what was it, transparent color index, transparent color flag. And this will be false, and this can be 0. And then when we get these later on, we can just say that this transparent color flag equals transparent color flag, and same for those. And then when we're drawing, we can say that if this transparent color flag, so if we have a transparent color and pixel, which in this case is a code, equals this transparent color index, then do the drawing. So at the end here we still need to move the cursor along, but now we have a transparent color, and we'll put this back because we know that this is not our problem and it is causing us CPU issues. So when we we're still pausing. There we go. What's your problem? Oh, it's trying to finish processing. Let's open this up just to make sure that we're going with the cache disabled so we get the new version. Okay, I've done that the wrong way around, haven't I? I've inverted that. So if this is not equal to the transparent color index, then draw. Down. And that looks much better. So obviously we also seem to need a background color, something for it to be when we have a transparent pixel on top of nothing, because we haven't drawn anything yet. And I believe that is not in here. No background flag. Okay, well that's a mystery for another time. But you'll see that if we okay. One of the things that happens when we draw this is that we are CPU bound. We're in a single function call. So in our loop at the top, we do this whole while loop, and that does the whole file, including drawing every single image. And that's clearly a bit mad. Spilt tea on myself. Because we'll draw everything before the browser gets a chance to we'll write everything into the canvas before the browser gets to draw anything. So the browser will only draw the very last thing after it's taken, what was it, like 30 seconds to do everything. So instead what we're going to do is we're going to break this up a little bit just for testing purposes. This is not how we'll do it in the end. But I'm going to create a function here and we'll call it draw. So this is inside another function. So and we will change this loop to work on animation frame. So we'll say if this.parse data, so if it returns true, then request an animation frame to run this again, to do the draw again. Yeah? And then we set it going first time through. So this is still doing our loop. It will end as soon as parse data returns false, because we won't request another animation frame, so it will never call draw again. It will call draw the first time around to run this parse data. So we should now get a frame per data block, some of which will actually draw because there'll be image data. So this is a little crude, but this should give us some animation now, because it will just draw them through the file, and then it will stop when it gets to the end, because we don't restart animation. So let's see what happens. Oh, stupid. Oh, I'm still throwing that error, so we need to turn that off. Let's search for array. So here we go. You can see the image is changing slightly from frame to frame as we draw each image. You can see the brush is moving up, but it's still not right. Still not right. And I expect this is almost entirely down to us being not getting a full image of data out of the stream each time we read it. So that's pretty exciting. There you go. I've animated a GIF. Not all of a GIF, but some of a GIF, and I think that's pretty good. It deserves a sip of tea. But it's not right, and we need to find out why. So, is this finished? Yeah, I think that's finished. Yeah. I don't want it to be using up all my CPU when I should be using at least some of that for encoding this video. So what could it be? So we know that we're reading out a lot of data in image bytes. Reading out a lot of data in image bytes that we need to decode, but then once we've run the decode process, we're getting out only a very small number of indices, relatively speaking, like 7%. So if we look at our decode function, wherever that is, that one, this one. What could cause this to end early? Well, so the buffer that we get here has the full set of data. So we're clearly not reading to the end of that. So what are the things that could cause this function to end? One, we get the end code. That could be a reason why we stop. And two, there is actually a thing here where I've got to return, because this check might come out. So I expect that whenever we get a code that we've never seen before, it should be the next code that we're going to add to the dictionary. That should be how it works. So here where we're reading here, so on this line we receive a code 6 which we have not found, is not found in the dictionary, and the next thing we add to the dictionary is code 6, and then here we read a code 9, and the next thing we're adding to the dictionary is a 9. And so I added this check in to check that that was always the case, but the spec doesn't actually say that needs to be the case. So maybe that's where our bug is. So let us first, well, okay. In order to not use up tons of CPU time, we'll put that error back in to stop us. And we're also going to find where we do that check. So what does it say? Unknown code, not next in sequence. Okay, so let's look for the word sequence. So we're going to look to see if this ever happens, basically. Could this be interesting? So this may be preventing us from getting the rest of an image, because here we can see that what we're expecting to be next, 512, is not the code that we get, 773. Now, the fact that next is 512 makes me extremely suspicious, because that is 2 to the power 9. That is an exact power of 2. Not... Yeah, I mean, it could be randomly that, but it seems sort of unlikely. Especially since here, we have been adding things, receiving codes roughly in this kind of area, up to the sort of 500 mark, and then suddenly 773. So I guess I really want to know how we got here. How do we get to the situation where we have, where we're reading this? Well, first let's see if this is the problem. So we'll just comment this whole thing out. And if this is the problem, then we should get a full image, right? I mean, maybe a wrong image if there's some sort of bug, but it means that we shouldn't be stopping early anymore. Yeah. And clearly not. In fact, this last couple of lines looks messed up. So, no, we have a bug. We have a bug. And it is something to do with when this .next gets to 512. When that happens, our check that we just moved should be true. We should have just increased the code size before that happened. So we'll put a breakpoint in here, and we should get this. So first of all, in fact, exactly then. So this .next is 512. Which is this, so code size is going to go up to be 10, which is not more than 12, and then we read a new code. And so far this seems pretty straightforward, but presumably at the very next time that we get a code that we don't know about, the code is 545, and this .next is 545. That's very interesting. That's very interesting. So, we saw that this .next was 512, and the next code we read was 700 and something. Here we see that next code has already passed 512. Okay, so let's put in a conditional breakpoint here, where this .next equals 512. So this should fire the breakpoint when we come through here and we get a code that we don't know, and the next code is supposed to be 512. Because I have a theory that this is happening more than once. Okay, so this .next is 512, code size goes up. And then we get through here, our code is, where's code? Oh, 773. So it is happening here. This is the first time it happened. So, okay. I'm a little confused. Let me run this again. Sorry. No, I want this. So this .next is 512. Then I run through here, and we get some code, and we add something to the dictionary. So this .next is now 513. Okay? This .next is 513. So it was past 512. And, as far as I'm aware, this .next only gets updated in two places. Here and here. But maybe I'm wrong. Let's see what happens. This code size goes up again. Oh. Right, so we must have had a clear code. We've had a clear code in between, so it's not the first time this happens. Let's restart that. How many times do we get a clear code? 1, 2, and the second time we get a clear code, shortly after that, we get an error. So does that mean that we're not clearing things correctly when we get this clear code? What do we do? We set the code size back to the initial code size. So the dictionary, excuse me, to be empty. And we set this .next to be here, which straight away is going to be 512. No. 158. So we do a clear code, and then it goes wrong somehow. Let me indulge my curiosity here. What if, when we get a clear code, we return? Let's return whatever the result is. Oh, except the first time. Very first time. So if last equals null, which is something that will be true only the very first time through, is not equal to null, sorry. Because the very first code we receive is a clear code. So you can see that the first time we get a clear is about when we've got all of the image data that we're successfully decoding. We don't really get anything useful after that, so it's the clear that is the problem. What could be the issue here? That's a good question, because this was not super well specified. One of the things we know is that all of the decoding parameters get reset. And as far as I'm aware, those decoding parameters are next, code size, the dictionary. What if last needs to be cleared too? Like, we had some documentation here. Does this tell us? Clear. First value in the code stream should be a clear code. We should initialize our code table. We need to know how many cores are in a table. Set up codes 0 to 3 to each of the 4 cores. Add a clear code and an end of information code. But it doesn't tell us what to do the next time we get a clear code, because it never happens again in this particular example. So, have a look in the spec again. Clear code. Oh, it's clearly what we were looking for at the end of last time, apparently. When the decoder's table is full, it must not change the table until a clear code is received. Code size is that of the maximum code size. Okay, so this is the very top of the spec, and it's just saying, hey, some people don't handle this correctly, so you should do something different. What can we do instead? Let's look further in the document for clear code. So, a special clear code is defined which resets all compression decompression parameters. For example, if the code size indicated was 4, clear code would be blah. But it doesn't tell us what to do when we receive one. It says all parameters without saying what the parameters are. Because I wonder if the last thing we got needs to be cleared. I mean, we can guess that. So let's say last equals null. Oops. It's the only thing that we pass through. No, we have this adding things to this stream, but I don't think stream is used anywhere. Yeah, that's nonsense. Oops. Can ignore that. I'm not sure what was going through my head when we added that, but it's not needed. Ah, background color index. We do have a background color index. It's just in a different part of the file. Awesome. So, okay, before, just while I remember, when we first get our canvas and we read the background color index, yeah, there, what we're going to do is we're going to say that context.fillRect I'm going to fill the whole canvas, and we're going to set the color, the fill style, to be, and it's going to be, oh no, we can't do it here because we need to read from the global color table, and that doesn't get read yet. This happens after here. This is super slow, but we'll do it anyway. Given how much we, well, at least I, write code and then it turns out to be junk, this is why I'm spending zero time trying to think about how to do this properly, like how we'll do it in the end. I just want to see that it works, and then we can fix it from there. I don't want to spend any time on making this like efficient first run through. Okay, so there are a bunch of questions in the chat, and I will come to the one about array buffers at the end because it is slightly off topic. But so, question from Oliver: in the end, will all frames be kept in memory for smooth looping, or is there another way? So I will keep all of the frames in memory, and there are two ways I can do that. One of them is more efficient than the other. So I can keep a canvas that has the image drawn to it. So I have separate canvases, one for each frame, and then we draw the contents of that onto the main canvas in each frame, the appropriate one. Or I can keep the bytes, the color information bytes, the image data around in separate arrays, and then set that onto the canvas, which is very slightly more efficient. because the canvas keeps a whole bunch of extra state around. Canvas is a DOM element, so there's a lot of extra information around about it. But we'll probably start with the canvas and then move on to doing it with just data. Because as I say, doing it the more efficient way, if it takes more time, you may be wasting any time that you spend, because you might do it differently in the end. So this is going to be, we already have code that does something like this. When we draw, cannot, okay. Perfect. Except instead of saying pixel, this is all going to be background color index. So we should see here that the background, oh dear. Less successful than I hoped. Look at it go. Did I take out the error here? Oh. Why is this taking so long now? What have I changed? Well, here's something that might speed things up. One of the things that's happening here is we're writing numbers out to the console on every frame. And that's actually pretty expensive. So we might actually do better just to get rid of that. Nope. Mind of its own. Throw. Just throw. Did I take out some sort of check that would let it finish early? Yeah, this one. Right, okay. Stop. Okay, we need to work out what I've just done there, because so the thing I actually just changed, where I'm drawing to the rectangle, only happens once. Just once in the whole program. That can't be what's causing the real issue here. And in fact, we can see that it's complete. It goes green very quickly. Something is not happy here. So let me set a breakpoint. Oh, I can't even set breakpoints. Or can I? Are they created? Okay. I killed it. You see, most websites don't cause Chrome trouble at all. I seem to be able to get into these infinite loops and crashes. Like, it is a regular part of my daily working life. Maybe 2 or 3 times a week, I will be working on something that causes me to constantly hit these loops. Does that say things about me? I think it says things about me. Rather than the stuff that I work on. I should have learned by now how to avoid getting caught out by this. Okay, So this doesn't seem to be showing anything actually taking up a lot of time. No, that was wrong. That was wrong. I need to open up the tab, open up the inspector, and then I'm going to hit pause and then do that. Oh, bloody hell. Okay. Okay. Right, okay. So really? Why isn't that hitting like straight away? What did I change? So I must have changed something somewhere that means that it no longer exits from somewhere. So is it in the decode here? I did comment something out. Maybe it was that. Okay. Seems like it might be better. Yeah, okay. So it was this bit where I set last to be... Oh. Where I set last to be null only in the case where it was null already. So when I was setting last to be null before, that just broke everything. That is clearly not what we do when we clear. So what do we do? Mysterious. So I think last time we deliberately did this where we reset the code size. And that's interesting. So if I don't reset the code size, that doesn't make things any better. And it doesn't make them any worse. Yeah, it's basically as soon as we get to a clear, it goes wrong. It goes wrong. It also means that I think this check here is valid. I think maybe we should be throwing an error here. I think that if the code, if any unknown code we receive should always be the same code as the next item that should go in the dictionary. And if that isn't the case, that's probably whatever bug we have rearing its head. Okay, sorry. Getting news on my watch, which is funny but not relevant to this stream. Okay. So what do we do? What do we do? Okay, GIF, clear code. Oops. No, I suppose you should, but wait a minute. I don't know what smartwatch I have. It's a smartwatch. Huawei? Possibly? Sorry, for the purposes of the video that comes after the stream, I shouldn't just answer questions from the chat without saying what the question is. I'll rest. I said 4 streams in and we still don't know what smartwatch you have. It's an Android Wear watch. Let's say that. That's definitely true. Okay, this is not super relevant. What's in a GIF? This seems like it's the same information. It's the same. This is the same article was already seen, but maybe it's a slightly different version. Nope. What do we clear? Understanding gift. Oh no, I don't want that. I don't really want to look at the source code of anyone else's GIF decoder. That feels like cheating. We should be able to work this out, right? But no. Oh, it's not a GIF clear code, is it? It's an LZW clear code. LZW and clear. Oops. Clear code is blah. A special clear code is defined which resets all compression decompression parameters and tables to a startup state. Oh no, this is. I think this is the spec. This is. If not the spec, then what the spec is based on. So it's the same information. So this should be LZW. Reading documentation, it really is what most of development is, at least in my experience. But it's not fascinating. Not fascinating stream viewing, is it? So I'm gonna try and get through this quickly, and then we might just accept that there's something wrong and go on to draw something else instead. Sorry, we might go on to, like, I might move on to doing animation properly, even though it's not drawing correctly. Oof. Okay, let's see this then. This is in JavaScript. Dictionary results, dictionary size. Set everything in the dictionary. What to do? Oh, here's the decompress. What to do if there's a clear code. It doesn't even seem to handle it. If k equals dict size. Okay, so this is also doing the same same check that the next index and the so that the code and the next thing to put into the dictionary, if they are the same, then do whatever. Otherwise, return null. So that is a hey, that's not correct. Yeah, there's no handling of clear code here. None whatsoever. Yeah, nothing ever clears the dictionary. Impulsive Welch, which is what LZW stands for. When the table is cleared in response to a clear code, both encoder and decoder change the code width after the clear code back to the initial code width, starting with the code immediately following the clear code. Okay. That's good. That's what we're doing, isn't it? Clear. Start next is end code plus 1. Code size goes back to initial code size. Dictionary becomes empty, and then we fill it up with just the initial things. This is what we're doing. So maybe we are handling it correctly, and there's some other reason why things don't work after a clear. So what do I do? This dot clear. What would I have done if I hadn't received a clear? I would have added something to the result. Well, that's clearly not. It's clearly not the correct thing to do in the event of a clear. I would have added something to the dictionary, but again, that doesn't make sense because we're clearing the dictionary. Yeah, what would we add? Unless we add the last thing that we got. It's not what you do at the beginning of the reading. You read something off before you ever add anything to the dictionary. We always read a code that's outside of this. So I don't know. We set last. But when I was setting last to be null, that caused problems. That gave us an infinite loop. Let's see why. I want to understand this. I want to understand what's going on. So in here, when we first start, go through, we get a clear code immediately. But I want to find out what happens the next time. So we get a clear code. Oh. No, it's okay for the last to be null. It doesn't have to be an empty array. So the next code we get is 191. Dictionary is empty. That's great. This dot next. Wait a minute. Clear code is 256. End code is 257. This done next. Okay, it's 258. Fine. So that'll be in there. Last equals current. So there was sort of the possibility that would. I don't understand why last equals null would have broken it before. Because clearly that shouldn't affect anything. Unless it means that we never get to end code. So how far through? Oh, so we're reading position 10,000 of a buffer, which is 125,000 long. So let's, in our reader, let's just check here. add a breakpoint and say that this dot position is more than or equal to this dot buffer dot byte length. So if we go off the end of the buffer, which I think should have given us an error anyway, this will tell us, just to make sure that that's not what's happening. We get another clear code. Where are we up to now? Read up position still like 16,000. 21,000. So this looks like it should go on for a long time. One of the possibilities for an infinite loop would be if the buffer wasn't getting read, like if we had a clear code and that meant that we didn't move on in some way. No, that doesn't seem to make sense. Anytime we read a code, that should move on, move the state of the stream on a little bit. Just looking through my other notes and just seeing. Is there anything I forgot to do? No, this looks like we did everything. Yep. And this is clearly going on for forever. This is never stopping, and I can't break again, and I don't get it. Well, that's extremely disappointing. Extremely disappointing. Oh, we finally got a breakpoint. Code size is up to 12. Where we got to here? So the reader position 124255. Oh, we're actually really near the end. One, two, four, 325. 325. That's where I clicked randomly for. Oh, we were super close to the end, and I just hadn't let it run far enough apparently. So we have 230,400 indices to cover our 230,400 bytes, pixels. So actually, we're just really slow. Really, really slow. That's the problem here. The code is just super slow. It did produce the correct number of pixels in the end, which is not a great, endorsement of my bit reading code here. Okay, so we do that. It should have drawn all those things on, and then we throw Well, look at that. So, other than some stuff where the background color is supposed to be, which is not seeming correct, we're now drawing the whole image. So it was that we need to clear that last. So I guess the next real question here is, why is this so slow? I mean, this is ridiculous. Like, it's 230,000 entries in... Oh, I know what it'll be. I know what it'll be. Because our result is this array. It's a JavaScript array. And we do this concat. I mean, it sort of looks... okay, sorry. I'll not respond to the chat in the video. Sorry. So this is going to be really, really awfully slow, and it doesn't really have to be. So we know how big our result should be, don't we? So when we're going through and we are getting this data, we know the size, we know the image width and image height and the top position and the left position, so we know how many pixels we're supposed to be getting. So here's what we're going to do instead. We're going to say that our pixels is a new uint 8 array, because the indices that come back are all 0 to 255. You know, the actual output is 0 to 255. It's a new uint 8 array, and its size is going to be, well, it's going to be image width by image height? I'm not sure. So it's image width by image height. Is that the size of the canvas or the size that we're drawing? Because we have this top left. So if top and left were not 0, would we be drawing from here to width, or to here, from here to here plus width? I'm going to assume that for now I'm just going to say width and height, and we'll put a to-do. Image width times image height. Confirm that the image width height are the total area to be drawn, e.g. That the top left, top left values don't decrease the number of pixels. But this must give us a maximum. And then what we're going to do is we're going to pass in this buffer, oops, as our output. A bit like if you're doing C, you might pass in a struct to be filled in. That's what we're going to do here. We're going to allocate all of this memory, and we're going to pass in that allocated memory to the function. And then when we get up here, we need to actually receive that. So this is going to be the output this should, well, okay, I don't have JSON. It's not going to complain about the results, so. Okay, we only, oh, no, that's a different result. So we don't do that. We need an output index so that we know where we're writing to. We need, so let me just highlight where it does appear. So it's just here. So this, we don't actually need to return anything. And then here, for let I equals 0, I less than current dot length, I plus plus, output index plus plus equals current I. So instead of using a JavaScript array, which is going to be rebuilt and reallocated over and over and over again, 230,000 times, and instead of using concat, which does complicated things with checking whether the thing you've been putting is an array or a scalar or whatever, we're going to allocate the memory up front, and we're just going to write in individual bytes into that array. That should speed up a lot of the writing operation. I mean, we're still using concat here, and we're still going to do it every time, but the things that we'll be doing it on will be very short arrays, so that should be a little bit easier. Yeah, this should cut down a lot of memory churn, a lot of reading and writing of memory. And then when we use this, as I said, we no longer get this. We're passing in the output buffer, so this is going to be pixels. Let's see what happens. Green is good. How long will it take for it to be not green? And also, since DevTools was closed, this is probably the old version of the code. So that's thank you, caching. Oh, I guess we can check that it seems to be working. All zeros so far. Oh dear. Does it actually start with all zeros? No, it doesn't, does it? Oh, maybe it does. Those all appear to be zeros. And that's just growing 0? Okay, we do get other values eventually. It's just a really long time before anything changes in the output. Phew! So our output index is 224, so that's like here, so we do start getting output that isn't zeros. Good. We'll go from clear to clear just so we can see how things are progressing. We get about 10,000 pixels per clear. See, that's 59,000, 67,000, 76,000. Yeah, about 10,000 pixels per clear code. We need to get up to about 230,000. We're only about halfway there. Let's leave it running and see what happens. Yeah, very nervous that this is all going to crash. Because you can't even set breakpoints and things. Once it's going, it's really hard to get it back. Oh, we're drawing. So that's clearly still super slow. What can we do about that? Well, what we can do is we can stick a... Oh, we never did overrun that. That's good. We'll stick another breakpoint in for the clear code. We'll say... We'll refresh. We'll wait until we get there. And then I'm going to start up recording. Oh. And then what happened? Did that ignore my breakpoint? I think that ignored my breakpoint. No, that didn't do anything. Okay, so it just put a modal up, which meant that it was hard to do anything with a breakpoint. So, okay. Let's refresh with the performance tab open. That seemed really fast. Why did that seem really fast? Tons of CPU time. 505 milliseconds. Doing all kinds of stuff, but it then left us with an image. Parse image descriptor. In fact, we read all of the images. Let's turn off screenshots here. Sometimes debugging this stuff is maddening. Why is it only fast when I have the performance profiler on? That is only doing one image because I'm erroring out after. Yeah, when I run this with performance profiler on, it stops relatively quickly. Does this... Oh, okay. Who knows? Who knows? Let's turn this off. And we can watch our animated GIF in all its glory. Or something close to glory. What just happened there? We hit a breakpoint, or... Oh, we hit a breakpoint. I don't know why that's even there. I must have accidentally clicked it. And you can see that as we draw frames in... As we draw frames in, the transparent pixels are picking up the correct background from the previous frame. You know, eventually it all gets written, it all works out correctly. Except for this bit here, which apparently never gets drawn. Interesting. Madness. And we seem to have stopped again. Oh no, we're not paused. Oh, we just reached the end of the image. We just reached the end of the image. So clearly we have a frame rate issue. And we have a transparent pixels issue. This, you can now see after only 4 weeks. This looks like we might be able to decode a GIF. So I think that changing how we do the output of the decode has made things faster, and that just when I first was refreshing, for some reason it wasn't loading it up from disk. The tiny little web server I use for testing this stuff, I didn't think it put in any caching headers, but I could be wrong. I must be wrong. Headers. Cache control, max edge 360, 3600. Okay. I don't understand caching headers enough, even though Jake Archibald on my team has talked about them a bunch. It just doesn't go in because it's mad. That's all I really remember about it. So why is our background color wrong? That's a good question. And why is it so slow? I mean, so later on, the gap between individual frames of a GIF is controlled by some information in the GIF, as is how to draw a next frame. So, oops, expect it to be that link, isn't it? So you actually get you get told which of the images is next, and hang on, probably wrong there. So no, you don't. Can't talk. So you get told how long should be between individual frames of the GIF. And in our case, we actually know this because it is in the delay time. I believe that delay time here, which is 6, that's how many milliseconds between frames. That doesn't sound right, does it? The graphics control the next 2 bytes of the delay time. Unsigned integer, number of hundredths of a second to wait before moving on to the next scene. So that's actually 60 milliseconds between consecutive frames, which is handily not a good number at all, because we get 16.6 millisecond frames, so it's one GIF frame in almost every 4 actual frames that we're drawing, but we can work around that. But at the moment, obviously, this is not going to help us at all, because we are not getting anything like we're not drawing anything like fast enough to keep up with that. I shouldn't have left that go. The profile becomes enormous. Here we go. So yeah, our frame rate is like atrocious. 2 or 3 frames per second. So I guess it's time to do some digging into why it's so slow. I think that's the next important thing. So what are our most expensive calls? So self-time parse image descriptor. Interesting. So when we come into parse image descriptor, we're spending 686 milliseconds. So of all the things that are currently on the screen here, let's zoom into a single frame. So of the 270 milliseconds that this frame takes, about half of it is spent on line 216 in this bit, the parse image descriptor. Not in something it calls, but in here. Now, fair enough. We can see here that this is all fill wrecked. So about half of the time is spent drawing. That's fair enough. The decode is actually very quick. 8.8 milliseconds used altogether, perhaps. The drawing then takes 4 seconds. These numbers, I'm not sure what they're relative to. This is clearly not per frame. Is it for the entire recording? I assume it's for the entire recording. That yes, but they should work relative to each other, whatever they are. So yeah, we spend 32 milliseconds in total just creating the arrays. The lights are going out. That seems something worth investigating, though that's still not impossible to deal with. 32 milliseconds over, several frames. Yeah, so I guess it's time to look at drawing performance, or how to draw more performantly. Oh, that's the actual GIF. That's not ours. I thought that was suddenly very smooth. That's Chrome's GIF decoder. So how can we draw to a canvas very quickly? Certainly not by drawing a rectangle, a 1x1 rectangle for every single pixel on the screen. That is mad, and certainly not by calling this setting fill style here like this. It's not actually as slow as I thought it would be. I'll be honest. I thought this would be much worse. Much worse. So what we're going to do instead is we're going to get hold of an image data object for the canvas, and I think we can just do this straight up outside here. Okay, I'm going to let image data. The reason we're going to do that is because if the canvas changes size, we need a new image data object. So do we change the width anywhere else? No, just one time. This is the only place we do it. So here we say that image data equals context dot get image data. Boom. And then we say that we want the whole screen, well, the whole canvas, sorry. And then when we want to actually draw to the canvas, what we're going to do is, so every time we do this, I'm going to say that we context.put put image data, image data, and that will be 0, 0. We only have to set those two. So this is the destination. This is where in the canvas this image data should go. So the actual drawing is going to be all done here, except for this, which I'm happy to leave. I mean, it's clearly something is wrong with the background color, doing something wrong. Not sure what it is. Yeah, so something we do only once, where we fill the whole screen with a rectangle. I'm happy for that to happen there. Now, when we actually go through and get the pixel data, we no longer want to write out the we no longer want to get the to do any of this. We just want to update the image data. So the image data contains an array buffer, like we've been using already. And the format of the array buffer, hopefully, so our color table contains the data as red, then green, then blue. And we need to just make sure that when we write into the image data for the canvas, that we write into that in the correct order. And I hope it's the same order. It's either RGBA or ABGR. I forget which way around it is. Image data. Oops. Image data dot data, because obviously something that's called a data would have a data property. So image data dot data is uint data rate. Let's confirm confirm that. So here we're actually going to do this loop and nothing will get drawn. Console.log image data. We'll just confirm to ourselves, yep, so it's a uint8 clamped array, 921600, which if we divide that by 4, because it's 4 bytes per pixel, gives us the same 230,000 that we expect it to be, so that's cool. So we say that image data. Ooh, so at the moment, because when we were setting the drawing the rectangles, we had to know the x and y position, and obviously they wrap as you go along. You know, you start on line 1 and you end up on line 2, and so you have to do all this where you allocate with work out where the x and y should be based on which iteration through you are. We don't need to do that. Now we can make this. We can say that let index equals 0. Now we're going to say that image data we're just going to do them in order. We don't have to. We're just going to fill the image data buffer in order with whatever we've got, and it should match 1-to-1. We don't actually have to think about it anymore about exactly where to write in, and those will actually help us with performance too. So it's going to be index times 4. Equals red. Plus 1, plus 2. That's going to be the green, and the blue, and then the plus 3, the alpha. We just want to set that to be 255 to mean that we're actually drawing it. Let's see what happens. Oh. Turn off the console log because that's going to take up a lot of time. Nope. What have I done? Am I setting the image data? Oh, I'm not updating the index. You can see I've drawn 1 pixel, a single pixel on the top. I need to actually increment index, and I need to do that regardless of whether it's a transparent pixel or not. So I'm drawing in the right place. Much better. Look at that. So let's get rid of some of these more other console logs that happen every frame. What's this one? Go control extension. Yep, get rid of that. Has local table, yeah, don't care. We'd get an error if it did. Magical. Oh, so because when I draw no, why does it go white now instead of green? Because for the transparent ones, I don't draw anything. Oh, okay. When I take the image data, it has all of the pixels in it, but I'm obviously taking it before I draw the background in. I think that's the issue. So yeah, that has made a huge performance difference. Oops. Yeah, drawing 230,000 rectangles takes loads more time than writing 230,000 times 4 bytes into an array buffer. You know, just copying memory is super cheap. It's kind of disappointing. We could actually change the way that we make our global color table to match better. So that when we're doing this copying, because it is in the same order, it's the exact same order, it would be nice if we could read out the so if the global color table was a uint32 array with the highest order bits being 0 or or being 1 for the alpha, then we could actually get a hold of the image data buffer as a uint32 array, and then we'd just be copying one number per pixel. And we wouldn't have to do this where we read out 3 numbers and we write out 4 numbers. We could just read 1 number per pixel instead. But this is now good enough to start thinking about other things. So let's profile this again. What's our performance? Okay, so it's still bad. You can still see this huge amount of... is that orange? I think it's orange. Again, I'm colorblind, so apologies. So we get some really quick frames, and that'll be where we're not actually decoding image data. Because if you remember, we fire an animation frame for every block we read. So if we zoom in here, we should find that we call... and we do a draw, but the parse data must be for something very small. It hasn't even appeared in the performance trace. It's too little work for it to actually bother telling us about. But then here we have the ones where it is decoding information. And let's see where the time goes. So now self-time is in decode. Cool. So now the majority of the time appears to be in the LZW reader, which is where I assumed the time would all be spent before. Now I don't always know how to read this. So here we can see pretty obviously there's this 1.2 seconds being spent on this line. Really? Really? The most expensive thing we've got is this, where we check whether this .next is not equal to code. Like, those two are numbers. Why is that so much slower than... in fact, it's saying we've got 200 milliseconds spent on this line, and that never happens. That never happens. So... what are you talking about, Chrome? What are you talking about? If we assign the... this doesn't... So maybe this 0.3 goes up here to the buffer, and the 0.1 there. And this would be let code, let last. Although why would that be 90 milliseconds? Yeah, I don't know. Let's try it again. Oh, sorry, we need to actually record the profile. Yeah, so it still reckons that I'm spending 150 milliseconds on a line that clearly never gets run. So there may be a bug in Chrome here that I should file. I have no idea what I'm going to write in the bug report. Maybe I could upload a clip of this video where I show it, because that's pretty mad. It's wrong. Yeah, these don't seem to line up properly at all. So that's kind of annoying, because it means that we can't tell which line is actually causing the problem. So Oliver is saying, can we try in Canary? That is a good question. Do we have Canary on here? We do. What? Yep, whatever. Yeah. Magic. Love it. Everything's a bit smaller in Canary. Come on. Oh, it doesn't... Okay, so Canary is not capturing by default when you refresh. Let me make this bigger so people can see. Make it ridiculously big like it is on the other window. That might be too ridiculously big. We'll see. Here we are. Decode. No, it has the same thing. 197 milliseconds on the line that never runs. This is exactly the same. So whatever it is still a bug in Canary. Either that or the information that this is giving me is not what I think it is. Like maybe I just don't understand this. But if I don't understand this, then who does? So that's still a bug. I mean, we can just double check, right? That never fires. Nightly. Canary is nightly. I could try it in Firefox. I don't know if its DevTools even give you this information. Not now. But I'm super curious to see what happens. I don't think we'll have... missing semicolon before statement. What? Oh, this might be a really old version that doesn't support something. I apologize to any Firefox people. This is probably not Firefox's fault. Where's the about Firefox? 49. What's the latest version of Firefox? Doesn't say. Stable release 51, maybe? Like 50. Someone in the chat is saying 56. Yeah, so I think we just have an old version of Firefox. I'm using async functions because I can. Yeah, that's that'll be the real issue here. Anyway, so decode is now our bottleneck. Let's just eyeball what we think might be slow in the decode. So this stuff happens just once. That's probably fine. It's the stuff that happens in the loop that's bad. Now, clear, we saw that happened about once every 10,000 codes. So that's going to be about 23 times altogether. So that's not going to be a huge contributor. And also, it's pretty. It's not very taxing. We build a dictionary of 256 items and set some variables. That shouldn't take very long at all. So these lines, these lines, these ones might be slow. These are the concats that we were talking about before. Concat is very slow because it takes an array and a thing that might be an array but might not, and creates a new array from all of the elements of the other things. Like, it does a lot of checks, it does a lot of copying. Um, I don't know necessarily what might be faster though. So I mean, the fastest thing we could do would be to magically know how big it needed to be, and we'd use an array buffer or something like that, where we're allocating the memory ourselves ahead of time. That doesn't seem feasible, at least not very easy. Well, hang on a moment. Here's something to consider. This is parse time. This is decoding time. We don't have to do this for every frame before we play the GIF. So I would definitely like to make this faster, but actually this is upfront time. So if we go, let's get rid of this. If we go over to stable and we load this up. Now Chrome obviously does a bang up job here. That is immediate. There's no 2 seconds while it decodes the GIF in Chrome. So it's presumably doing it on the fly, you know, as the frames come in. It is definitely faster. But we could fudge it. We could wait until we've decoded all of the frames, and then we create a new canvas or a new buffer for each frame, and we just set that whenever we draw and actually control the animation correctly. So in the chat, what is Chrome written in? Almost entirely C++, but obviously Chrome on Android has some Java, and Chrome on iOS has some Objective-C, and some parts of Chrome are actually written in JavaScript. So C++ is faster than JavaScript most of the time, but you can get pretty fast in JavaScript. We should not be more than one order of magnitude slower. So if it seems instant in Chrome, we should be able to do it in, you know, like 400 or 500 milliseconds in JavaScript. That's my gut feeling for how fast it could be. Yeah, and it's not just the language. Like, doing this sort of concat arrangement, you could do that in C++, but it would be slow there too. Yeah, it should be. We just need a faster way of thinking about it, and I don't want to hurt my brain. Like, I know this can be done in a much better way. Like, this is the sort of thing you could have as an interview question. You know, how do you make this thing faster? In fact, doing this in an interview for a C++ job would probably get you a no. Doing a big enough array buffer, but how big is big enough? Some of these strings could be, like, if you have a huge so what's the biggest it can grow? I guess each dictionary item could grow to be 4,096 elements long, plus or minus a couple. Yeah. So every time you add something to the dictionary, you could, let's say that every pixel was black and there were millions of them, so that you didn't run out of image before you ran out of dictionary space. You'd load up a 0 because that's the first pixel, and then the next round you'd load up another 0 and you'd write that out, and then you'd load up the 2 zeros and another 2 zeros, and you'd write out 3 zeros, and then you'd load up the 3 zeros and the 3 zeros, and you'd write out 4 zeros into the dictionary. And the thing you're writing into the dictionary would get 1 bigger each time. And we can have 4,096 entries in the dictionary, minus 2 because of the clear code and the end code. So roughly that order of magnitude. So we could do it so that each element of the dictionary was 4,100 bytes long. And then... But then how would we know what the end was? We'd have to store the length as like the first element or something. It would get complicated to do it that way. We'd want to do this sort of properly somehow. Anyway, as it happens, we are about out of time. So we have it so that our GIF displays almost correctly, and the animation plays through once. And it's not super slow. So even though we're missing our frame budget sort of Chrome wise, we're taking 60 milliseconds per frame. That's actually correct for this GIF. We got that 6 for the delay, which is hundreds of milliseconds, so that's 60 milliseconds per frame. And we coincidentally get about 60 milliseconds per frame. Somewhere between 50 and 70, 74. Yeah. So that's why the GIF looks correct. And once we've decoded it once, we can store those frames, and then when we loop round again, it won't be processing them again. And you can already see that actually, like, our startup time isn't very long. There's a brief pause. Let's record here and then refresh and see how big that pause is. So this is the refresh. And this is when we start drawing again. It's, let's say, 500 milliseconds, something like that. So 500 milliseconds from the refresh. In fact, from the refresh is probably not the right time because we're still drawing here. When does the response finish? So it's actually very quick, 200 milliseconds maybe from... Oh, in fact, we have when the image loads. It takes us 176 milliseconds to get something onto the screen. Just 176 milliseconds. Which is pretty good. So we could speed things up even more. I've been extremely sloppy so far. We can speed things up. We can figure out what's going on with those transparent pixels. We can rearrange some of the code because I'm not really happy with the way the code is arranged, but I didn't want to spend any time on it until we were getting closer. So I think we'll probably have one more session of GIF decoding next week, while we fix some of that stuff, and then I'll have a think about what I might want to stream next. So thank you very much, everyone, for coming along. Before I go, are there any questions? And obviously I have to wait a moment because of the lag between me speaking and you guys hearing it. Oh, where was it? So there was a question. Any idea why getting a single bit from an array buffer is tricky at the moment? Can you clarify? That's from Oliver Dunk. Can you clarify whether you mean that... So are you asking why the browser doesn't have that built in? Or are you asking why this is tricky? I assume you're talking about why it's not like built into the browser and you have to do it yourself. So it's fundamentally a thing that computers don't do. Yeah, so the array buffers that we have, uint8 array, uint16 array, uint32 array, and then float 16 and 32. Is there a uint64 array, and then the non-unsigned, the signed ones? Those are created. Those were actually brought in by Kronos, which is the standards body that handles OpenGL. They were brought in to handle the kinds of data that was needed for WebGL. So when they were thinking about adding these things, they had a particular use case in mind, which is WebGL, and it does not need bits. None of the API surface there uses bits. Now, some of the programs written for OpenGL might need them, but the API didn't. So they wouldn't have thought to do it. But fundamentally, the way that processors work makes it awkward. So when you're reading data, when the processor is reading data from memory, it has a particular size that it reads things in it. And that on a 64-bit processor is probably 64 bits. So it's actually inefficient to read anything smaller than 64 bits at a time. And when you have an instruction that reads a byte, there's actually a performance penalty for doing that. And there are no processor instructions for reading a single bit. Yeah, so it's slow to read a byte, particularly if it's not aligned on a nice boundary. And then reading a bit isn't even implemented on the processor. So it's something that no programming language that I'm aware of actually has, where you can read a single bit. That's probably not true. I think when I did my Game Boy emulator, you could set and get individual bits on the Z80. So okay, there are processors that implement it, but not common desktop or phone processors. And it's just not something that people do a lot of. So if you're doing a PNG decoder or an LZW decoder, those are those data formats have data packed specifically for how compact it can be, not because it's easy to read. The computer is designed to do bytes or 8, 16, 32 or 64-bit reads, with 64-bit reads probably being faster. Yeah, I think I may have rambled on that one. So there are only a few times when I've actually done bitwise reading bits. One was for a deflate reader, deflate being the compression scheme used in zips and PNGs and gzip and Flash, like SWF files. Deflate is used all over the place. And then here using LZW. And I happen to have done the deflate case a couple of times. But that's it. That's the only times I've ever read things bits at a time. Yeah. So it doesn't seem like something that needs to be a standard feature. So Oliver is asking, is mentioning that he got stuck doing deflate. Any tips? The spec for deflate is actually really good. The GIF spec I found to be a bit there are a couple of things like exactly what gets cleared by a clear code that was not properly explained, there's no like example data. But deflate I found the spec to be very useful, and then the Wikipedia page on Huffman coding. Anyway, cool. Thank you very much for joining me. and I will see you next time.